I got a haircut. So we're finally going to be able to talk about derivatives. We're going to see how all this limit business allows us to talk about derivatives. And let's remember that one of the ways that we think about derivatives is in terms of tangent lines to curves. So let's recall that to find the slope of a tangent line, so if this is some curve, this black curve, I'm looking for a tangent line at a point which is represented by this blue line right here. Well, we approximate the tangent by closer and closer secant lines. To get the secant line, I take the point on the tangent and one other point on the curve. That allows me to find the slope. That's represented by these red lines here. And as we let this second point get closer and closer to our original point, these secant lines sort of swivel up to our tangent line. And that should be able to allow us to find the slope of the tangent line. Let's remember that the slope of the secant between our fixed points c, f of c, and x, f of x, which is the second point on the curve, is given by the difference of y coordinates, f of x minus f of c, over the difference of x coordinates, x minus c. So to get the slope, we let x approach c. That's a limit. So the slope of the tangent line is given by the limit as x approaches c of f of x minus f of c divided by x minus c. So let's do an example. Let's find the equation of the tangent line to y equal to x squared at x equal to 1. Now I think we've already done this problem a couple of times, but most of the time that we've done it by sort of approximating the limit instead of actually evaluating it. So let's actually sit down and evaluate it. So here f of x is x squared. The point that I'm looking at is c equal to 1, and the value of the function at 1 is 1. So I evaluate f of x minus f of c over x minus c. F of x is x squared, c is 1, x is x, and f of 1 is 1. Well, the problem with this limit is if I plug in 1, I get 0 divided by 0. We've run into that. We know that when we have 0 divided by 0, we can often factor and then cancel. In fact, since we have polynomials here, we will definitely be able to do that. So I factor the top into x minus 1 times x plus 1. The bottom is a linear polynomial, so I can't factor it. I get a common factor of x minus 1, which cancel out, which leaves me with the limit as x approaches 1 of x plus 1, which is equal to 2. We approximated it to be 2 before. Now we are literally evaluating this to be 2. Then we plug this into our, say, point slope form, which gives us the equation y minus 1 is 2 times x minus 1. And if you want to, you can put that into slope-intercept form, which is y equal to 2x minus 1. Now we have an alternate formula for computing the slope of a tangent line. And what we do is instead of writing it as f of x, we rewrite x as c plus h. That is, we're thinking of x as close to the value c, just a little bit bigger than c. It's c plus h. And here h is some parameter that is tending towards 0, some little difference that is tending towards 0. So that means that the second point has coordinates c plus h and f of c plus h. That makes the top look a little bit more complex. It's now f of c plus h minus f of c. But the bottom becomes a lot simpler, which is just h, because that's just the difference between these two x coordinates. I went from c to c plus h. Note that technically h could also be negative, so I shouldn't be talking about it as a distance. If h is negative, then when I add to c, I get a point towards the left, but that's okay because when we talk about limits, we like to imagine things coming from both sides. So let's use this alternate formula to find the slope of the tangent to the curve y equal to 3 over x at x equal to 3. So here's a picture of the curve. I've drawn in blue the tangent line, and in red I've drawn a secant line. And here I'm showing that h can actually be negative. If I take a negative value for h and I add it to 3, 3 plus h is to the left. Okay, so f of x here is going to be 3 over x. C is equal to 3. F of c, which is f of 3, is 1. And when I add h to 3, f of 3 plus h is 3 divided by whatever's inside, 3 over 3 plus h. So that means that I take f of c plus h minus f of c, which is 3 over 3 plus h minus 1, and divide that all by h. And I take the limit as h goes to 0. Now we did one example like this I don't know if we actually did it in class, but it was on one of the problem sets. It wasn't graded though. How do you deal with a limit like this? Well, I know I should be able to get some sort of cancellation, because if I plug 0 into the top, I get 3 over 3 minus 1, which is 0, and the bottom I get 0, 2. However, the top is written as a difference right now. For me to begin to think about trying to factor out an h on top, I need to be able to write this as a single fraction. Well, I get a common denominator. The only denominator in town is 3 plus h, so I rewrite 1 as 3 plus h over 3 plus h. Now I can subtract 3 plus h from 3, which leaves me with negative h over 3 plus h all over h, which I'm going to rewrite as h over 1. Why? Because it's the ratio now of two fractions, which gives me negative h over 3 plus h times 1 over h. This h up here and this h down here cancel with each other, leaving me with the limit as h goes to 0 of negative 1 over 3 plus h. And now, this is a rational function which is defined when h is equal to 0, so I can just plug it in. And I get negative 1/3. Does that make sense? Well, our secant line looks like it has a negative slope. Good. That's correct. Also, this means that if x goes down 1, if y goes down 1, x goes over 3. And it looks kind of like, down 1 over 3 between the y-intercept and the point on the slope. So, or the point on the curve that we're concerned with. So, seems reasonable to me. It would be useful for you, if you'd like, to just take a moment to compute the equation of the tangent line, given that we are at the point 3, 1 and have slope negative 1/3. Okay, so our other interpretation of derivative was a rate of change, and the sort of fundamental rate of change that we were thinking about was velocity, which is the rate of change of position with respect to time. So I'm going to let s of t be the position of an object at time t along the axis. The average velocity of a time interval of duration h starting at time t equal to c, so starting at time c and then ending h seconds in the future, which is c plus h, is given by this. The difference between the two positions at time c plus h and c divided by the length of the time interval, which is h. We had a problem very much like this on the second homework set, I think. Anyways, so how do we get instantaneous velocity? We let the length of the time interval go to 0, so we let h go to 0. That means that the velocity at time c is the limit as h goes to 0 of s of c plus h minus s of c, all divided by h. And does this look familiar? Hint. It's the same formula as for the slope of the tangent line. So let's do a velocity problem. Let's let s of t be 450 minus 4.9 times t squared, and this represents, say, the height of an object in meters, t seconds after being dropped from 450 meters. So let's find the velocity at time 5. So here c is equal to 5, and we're looking to compute the limit as h goes to 0 of s of 5 plus h minus s of 5, all divided by h. I replace these guys in the formula for s. So I got 450 minus 4.9 times 5 plus h squared minus 450 minus 4.9 times 5 squared, all divided by h. Now these 450s here will cancel out, and once I expand out this polynomial inside here, I'm left with negative 4.9 times 25 plus 50h plus h squared plus 4.9 times 25. This negative 4.9 times 25 and this 4.9 times 25 will cancel out, leaving me with just negative 4.9 times 50h plus h squared. I'm not going to multiply through because I don't like dealing with messy numbers. Now I see that I've got a common factor of h that I can pull out. So I pull out the h upstairs, and that can cancel with the h downstairs, leaving me with the limit as h goes to 0 of negative 4.9 times 50 plus h. Now I can just plug in h equal to 0, which gives me negative 4.9 times 50, or negative 245 meters per second. I assume that's fast. So here's your question for this video. Let's let the same function be in play. S of t is 450 minus 4.9 t squared. Let's find the instantaneous velocity when this object hits the ground, which is when s of t is equal to 0. There are really two steps here. First, you need to find the correct value of t that gives s of t equal to 0. And then second, you've got to plug that into the instantaneous velocity formula and figure out what that is equal to. Okay, so this expression, the limit as h goes to 0 of f of c plus h minus f of c over h, has appeared in two contexts, as the slope of a tangent line and as an instantaneous rate of change. And that is supposed to be what the derivative is. So that's our definition. The derivative of f of x at c is given by the limit as h goes to 0 of f of c plus h minus f of c divided by h. We denote this quantity by f and then a little sort of apostrophe, which we call prime, so f prime of c. We read this as f prime of c, but it's just like function notation, but you put a little line there. And again, the derivative is the slope of the tangent. It is the instantaneous rate of change. So we've already computed derivatives for a few functions at a few specific points in the context of tangent lines and velocities. Now let's see how we can actually compute the derivative at every single point at the same time. And this is really where this formulation of the rate of change, the derivative, makes sense. Having the h on the bottom by itself instead of x minus c or whatever makes it a lot easier to factor and cancel. Okay, so let's find the f prime of c, where f of x is x squared minus 8x plus 9. By definition, f prime of c is given by this formula, and I plug in c plus h into f of x to get c plus h squared minus 8 times c plus h plus 9. And then I plug in c into here, and I subtract that quantity, c squared minus 8c plus 9 divided by h. Now I'm going to multiply this all out, and I'm left with c squared plus 2ch plus h squared coming from that, minus 8c minus 8h coming from that, plus 9. And then I distribute the negative through this expression to get minus c squared plus 8c minus 9 over h. There's a lot of cancellation that happens now. I combine like terms. C squared minus c squared goes away, minus 8c and plus 8c goes away, and plus 9 and minus 9 go away, leaving me with 2ch plus h squared minus 8h all divided by h. Okay, now what I'm left with is something that has a factor of h on top. I pull that out, and I've got 2c plus h minus 8 times h over h. The h's cancel, leaving me with the limit as h goes to 0 of 2c plus h minus 8. Now, h is the only thing that is moving here. C we're imagining as a fixed constant. So that's okay for a final formula to have a c in it. All we care about is saying, okay, wherever I see an h, we'll place it with 0, and I'm left with 2c minus 8.